Real-life comparators are digital, meaning the output is either high or low, and there is no in-between values. Unlike the Minecraft comparator where it's able to show distinct levels. And so here I have the dual op-amp, the LM358N. Dual op-amp because it has a separate op-amp on each side. Depending on how you set up these resistors will determine what operation you will be doing. And so right now it's set up to emulate a comparator with 5 volts positive, the ground pin connected to ground, and an LED with a current limiting resistor connected to the output. Right now on the inverting pin, it's connected directly to ground, and on the non-inverting pin, it's also connected to ground. When the non-inverting gets disconnected from ground and results in a higher voltage, the output will be high, but instead of sending out the input voltage, it actually sends out a lower voltage. Op-amps are analog, meaning that they operate in a full range of voltages. Right here, the inverting is connected to around 3.3 volts, and so as soon as the non-inverting goes above the 3.3 volts, then the output will result in a high output. And once it drops below 3.3, it results in a low output. Also, unlike the digital comparator, the op-amp is able to output the same signal it receives, named the voltage follower configuration, using multimeters in order to read the values without affecting the circuit. Here's the wiring that would be needed in order to create the subtraction mode of the comparator. In addition to the wiring, you would also need a negative power source. And so here I have a battery pack of around 3.6 volts with a positive terminal going to the ground of the other power source and the ground of the battery pack going to the ground of the dual op-amp. When connected in this configuration, the ground of the op-amp will be at negative 3.6 volts and the positive of the dual amp will have positive 5 volts. The negative power supply is needed in order to invert one of the signals to make it negative. The signal that's being inverted is half of 3.3 volts here through this voltage divider. Once the signal is inverted, it gets carried across to the other side where it will be added to this voltage here. The LED will begin to turn on at around 2.4 volts. And so by increasing the input voltage to around 3.5 volts, the sum of the voltages will be around 2.4 volts. There's a first signal of negative 1.1 volts and the second signal of around 3.6 volts for a total of 2.5 volts. And so now increasing the other voltage will increase the output voltage for a maximum of 3.55 volts. In order to simplify everything, I decided to use the Amiga 328P in order to condense everything down. In order to read the voltages, I have a pull down resistor that's connected to one of the analog pins. The resistor you use as a pull down is really important, and I made the mistake of using a 1000 ohm resistor. I recommend using at least a 10,000 since a lower resistance value will consume more amperage from the input signal, also greatly reducing the Schottky redstone dust signal. The construction is similar to the comparator. In order to open it up, the caps need to be removed. And now from the bottom, just gets pried out and shaken back and forth. And here I tried something a little bit different. I made an inlay this time instead of using any resin, and it seemed to work out pretty good. Now having a look at the circuitry, positive voltage comes in this line and everything gets grounded across after these resistors. In order to turn on the lights, pin number 2 gets connected here, and so when on, current flows through the LEDs, through this 400 ohm resistor, and down here is the switch, so when it's off it gets turned here, disconnecting the pad that goes to this LED, and when it gets switched here, the positive voltage flows through the LED and through this enameled wire to this pad, which is connected to this resistor here, and a separate enameled wire that runs down to the digital pin number 4 of the microcontroller. When current runs through LED, there will be a voltage that is read at pin number 4. If it detects voltage, it'll switch to the subtraction mode, but if it reads 0 volts, then it will be at default. The 4 bottom pins get connected to the modular top pins, and just like with the repeater, it gets connected to the microcontroller. In order to show the subtraction mode of the comparator, I'm using the lectern instead of having to make more of these redstone dust blocks. And so it condenses the redstone down to just one block instead of having to line up all these redstone dust. Here on this side, this lever connects a redstone dust, and so that loops back into here, giving a full signal to the comparator and turning off the signal since it's higher than the lectern signal. On this side, I'm actually using the old version of the Redstone desk. It has 5 volts going to this lever here, and when the lever gets connected, then it sends that 5 volts through a Schottky diode and into the comparator block. The 5 volts will also be able to go through the LED and down through the block pins in order to get grounded with the battery. Now, of course, it's easy to just swap the lectern with the lever, since all it's doing is just sending a 5 volt signal back. And in order to swap over the lectern, it just needs to be replaced with this top. Just like with the lectern block, the 2 wires get connected into the comparator block. So now when the lever is flicked, it sends 5 volts back into the comparator, outputting a full signal. Since the lectern has a redstone signal of 8, then when putting into subtraction mode, it'll subtract 8 of the redstone signal, leaving a final redstone signal of 7. Putting the comparator back to the default state will send out a full redstone signal, since the lectern signal is lower than the input. The easiest way to implement the right input would be to use 3 independent pins to read the right, the left, and the main input. If using the Schottky redstone design, you should be able to just have it on one single pin coming in from the right and also from the left. Since if one has a higher voltage after the Schottky diode than the other, then current cannot flow through the other circuit, keeping the same voltage value of that one circuit. So that's pretty much it. As always, if you have any questions, please let me know, and